Hello, in this video we will look at recurrence relations and how to solve the linear recurrence relations, both homogeneous and non-homogeneous. A recurrence relation for any sequence is basically an equation that expresses an, that is the last term of the recurrence sequence, in terms of one or more previous terms. The sequence is called solution of a recurrence relation if its terms satisfy the recurrence relation. Let us take an example of rabbits and how the reproduction of rabbits in this example can be modeled as Fibonacci series. So let us say that we have a pair of rabbits placed on an island, and this pair of a rabbit cannot breed until they are 2 months old. So find a recurrence relation for number of pairs of rabbits on the island after n months, assuming that these rabbits never die. So here we can understand that in the first month we have one pair of rabbit. In the second month we have the same pair of rabbit who cannot breed. In the third month we have that initial pair which can breed and produce one more pair. So this is a pair that the first pair produced. So at the end of the third month we have two pairs of rabbits on the island, which can be counted as the number of pairs of rabbits in the previous month plus number of pairs of rabbits reproduced, which is equal to the number of pairs of rabbits 2 months back. Okay, which is equal to number of pairs of rabbits 2 months back. So if we denote that this value, the value at this point, that is 2, can be calculated as 2 can be calculated as the nth element of the series as number of pairs on the island in the previous month plus number of months of pairs produced in this month, which is equal to number of pairs 2 months back, which is nothing but fn minus 2, with initial condition that the number of pairs in the first month, okay, the number of pairs in the first month is equal to 1, the number of pair in the second month is equal to 1. So this form of representation of rabbits reproduction on the island is nothing but a recurrence relation, which is expressed as addition of previous two elements of the series. Let us take another example of Tower of Hanai. Now, in Tower of Hanai, you have basically three pegs, and the initial condition of the problem is as shown in the figure at the top here. Okay, so initially we have all the discs arranged on one peg. The discs are such that they are of decreasing size. They are of decreasing size. There is a rule that you are allowed to move one disc at a time, and you cannot place a larger disc over a smaller disc. You have to, the goal of the problem is that using these two rules you have to get same arrangement of the disk onto the peg 2 or column 2. Now, to solve this particular problem, we can say that out of n number of disk we can move n minus 1 disk following the rules of the problem, that is the arrangement shown in figure here. That is, you have the larger disk left on the first peg, and you move all the disks to the peg 3, which is called as an auxiliary peg, following the rules of the problem. And let us say that the number of moves required to move these n minus 1 disk is hn minus 1. Now, using one move from peg 1 to peg 2, okay, we can move the larger disk. We can move the larger disk. Then we can solve the problem for n minus 1 disks. We can solve the problem for n minus 1 disk for movement from peg 3 to peg 2, peg 3 to peg 2 with additional hn minus 1 moves. So in general, how many moves we require to solve this particular problem? First hn minus 1 moves to move from peg 1 to peg 3, additional one move for the last disk to move from peg 1 to peg 2, and then hn minus 1 moves to move this remaining disk from peg 2 to peg 3. provided the rules of the problem are solved. The initial condition of the problem will be that the number of disks equal to 1, it requires one move to move from peg 1 to peg 2. So if we use a iterative solution to this, that is the n number of disks, the number of moves required to arrange n number of disks from peg 1 to peg 2, following the rules of the problem, is equal to 2hn minus 1 plus 1. Now, this hn minus 1 itself is a recursive problem and can be expressed as hn minus 1 is equal to 2 into hn minus 2 plus 1. Okay, 2 into hn minus 2 plus 1. Further, hn minus 2 can also be represented as 2 into hn minus 3 plus 1. So recursively or recurrently, we can follow this definition unless we reach to a problem where where h2 will be equal to 2h2 plus 1, sorry, 2h1 plus 1, where h1 is equal to 1, and then we could solve it again bottom up to get the number of moves for hn. So if we go on substituting this mathematically, we get a solution that to solve a problem of tower of ni, we require 2 raised to n minus 1 move. So imagine that your peg has three moves in the three disks in the initial condition. Then number of moves required to move from peg 1 to peg 2, following the rules of the problem, is is if n is equal to 3, it is 2 raised to n minus 1, that is 2 raised to 3 minus 1, that is there are 7 moves required. So we can express this problem through recurrence relation, and the recurrence relations can be further solved to have a general formula to calculate the number of moves. So let us continue understanding what is linear homogeneous recurrence relations and how to solve this linear homogeneous recurrence relations with constant coefficients, and then subsequently look at how to solve the linear non-homogeneous recurrence relation. So first let's understand what do we mean by a linear homogeneous recurrence relation. So a linear homogeneous recurrence relation is a relation in which an nth term of a sequence is expressed as one or more terms, previous terms of the same sequence. Or in other words, the n term is expressed as a combination of one or more previous k terms. Okay, previous k terms. Now this equation is linear because the RHS of this equation is sum of previous terms of the sequence, each multiplied by a function of n. And then it is homogeneous because there is no term that occurs that are not multiple of a of I, means there is no constant term. Okay, there is no constant term, and as an is expressed in terms of previous k terms, this linear homogeneous recurrence relation is called as a relation with degree k. Okay, the relation with degree k. Now these are few examples of recurrence relation. So first is basically calculating the principal earned at the end of the nth year at 11% per annum. Okay, which is a linear homogeneous recurrence relation of degree 1, as n is expressed as only previous one term of the sequence. The next one is Fibonacci series. So this second one, fn is equal to fn minus 1 plus fn minus 2, is linear homogeneous recurrence relation of degree 2, as the next element or nth element in the series is expressed as addition of the previous two elements of the series. The third is not a linear recurrence relation, as you have a square term into it. The second last is the typical tower of Ni recurrence relation, but this is not homogeneous because of this constant term 1. Okay, and then the last one is not a recurrence relation because the coefficient is not constant, it depends on the value of n. Now, how to solve this linear homogeneous recurrence relation? Uh, so the recurrence relation is n is equal to c1 an minus 1, c2 an minus 2 up to ck an minus k. That is, an is expressed as sum of previous k terms in the sequence. Sum of previous k terms in the sequence. Now, every recurrence relation is associated with a characteristic equation which is nothing but is represented by r raised to k, and therefore c1 an minus 1 is represented by c1 r raised to k minus 1. Okay, r raised to k minus 1. This equation is called as a characteristic equation, and we need to solve this equation to get root of the root of the equation, that is solve this characteristic equation to get the roots. So these characteristic roots are basically uh, used into further formula. Now, if we have a recurrence relation of degree 2, we have a recurrence relation of degree 2, then this is a standard characteristic equation, that is r square minus c1r minus c2 equal to 0, which has two distinct roots r1 and r2. Then then recurrence relation has a solution has a solution given by an is equal to alpha 1 r1 raised to n plus alpha 2 r2 raised to n, where r1 and r2 are roots of the characteristic equation. Alpha 1 and alpha 2 are constants, and n is equal to 0 1 2, which represents the position in the sequence an. Now, let us solve this linear recurrence relation. So, what we have here is an is equal to an minus 1 plus 2 an minus 2. Now, the characteristic equation associated with this is r raised to k minus r raised to k minus 1 minus 2r raised to k minus 2 equal to 0. Now, how many previous terms are used? There are two previous terms used to express an. So, k value is equal to 2. So, this equation becomes r square minus 1r minus 2 equal to 0 minus 1. So, solving this further, that is, we'll get the roots as r1 equal to 2 and r2 equal to minus 1. Now, now Now, the typical solution of distinct roots is given by an is equal to alpha 1 r1 raised to n plus alpha 2 r2 raised to n. So, in this equation, if you substitute values of r1 and r1 raised to n, that is alpha 1, 2 raised to n, and plus alpha 2 minus 1 raised to n, alpha 2 minus 1 raised to n. Now, using the initial conditions a0 and a1, we can further take this as at n equal to 0, this above equation becomes a0 equal to alpha 1 2 raised to 0 plus alpha 2 minus 1 raised to 0. A0 is equal to 2. So 2 is equal to alpha 1 minus alpha 2. And with n equal to 1, we get 7 is equal to 2 alpha 1, that is 2 raised to 1 into alpha 1 plus alpha 2 into minus 1 raised to 1. Okay, 2 alpha 1 minus alpha 2. If we solve the above two equations, if we solve the above two equations, we get alpha 1 is equal to, so if we solve this equation, let's name this equation as 1, name this as 2, name this as 3. If we solve 2 and 3, alpha 1 is equal to 3, alpha 2 is minus 1. Substitute these two values. Substitute these two values in equation 1. So in equation 1, if we substitute these values, we get an is equal to alpha 1 is equal to 3. So we get 3 into 2 raised to n plus minus 1 into minus 1 raised to n. So this is the final solution of the recurrence relation. Let us solve another problem. Now this is a problem for typical Fibonacci series where fn is equal to fn minus 1 plus fn minus 2. So Here again, the nth term is expressed as sum of previous two terms. So k value is equal to 2, and therefore we get this equation as r square minus r minus 1 equal to 0. Now, if we further solve this equation to get the characteristic roots, we get r1 is equal to 1 plus root 5 by 2, and r2 is equal to 1 minus root 5 by 2. We can put this as the roots are distinct. We can use the solution equation as alpha 1 r1 raised to n plus alpha 2 r2 raised to n. So solving this further, we get alpha 1 into 1 plus root 5 by 2 raised to n plus alpha 2 into 1 minus root 5 by 2 raised to n. Now solve these two equations for n equal to 0. We have f0 is equal to 0, which is equal to alpha 1 into 1 plus 5, 1 plus root 5 by 2 raised to 0, that is raised to 0 is 1. So alpha 1 plus 1 minus root 5 by 2 raised to 0, that is alpha 1 plus alpha 2 is equal to 0. Therefore we get alpha 2 is equal to minus alpha 1, and we get the second equation as at n equal to 1, 1 is equal to 1 plus root 5 by 2 alpha 1 plus 1 minus root 5 by 2 alpha 2. Using these two equations, simultaneously linear equations, if we solve them further, I'm not going to go into the details of this, but I can say that the alpha 1 is equal to 1 upon root 5, and alpha 2 is equal to minus 1 upon root 5, minus 1 upon root 5. So solve these two simultaneously linear equations to get the value of alpha 1 and alpha 2, and then substitute these two values in the equation. Let's say this is 1, so in this equation 1, and so we get the sequence solution for this. An is equal to 1 upon root 5, 1 plus root 5 by 2 raised to n plus minus 1 upon root 5, 1 minus root 5 by 2 raised to n. Now, the first two examples that we had solved, they were of the type where roots were distinct. That is, both R1 and R2 were distinct. And so, in general, if we have any recurrence relations expressed in terms of previous k terms, okay, expressed in terms of previous k terms, so instead of two terms, three terms, four terms, five terms, then in general, how is the solution equation? So in general, the solution equation is alpha 1 into r1 raised to n, that is the first root, alpha 2 into r2 raised to n, that is the second root, plus alpha k into rk raised to n. So if your characteristic equation has k distinct roots, then you can find the solution in general. The above two problems that we had seen, where the problem 2, that is the sequence element described or expressed as sum of previous two elements. Now there could be characteristic equations where the roots are repeated, that is both r1 and r2 value is same. So if r1 and r2 value is same, then we will be using the equation alpha r raised to n plus alpha 2 r raised to n into r raised to n for a linear recurrence relation of degree 2. So for a recurrence relation of degree 2, where the characteristic equation is r square minus c1r minus c2 equal to 0, we will be using a solution equation as alpha 1 r raised to n plus alpha 2 n r raised to n, where the roots are repeated, where the roots are repeated. So let us try to solve this particular problem. Here an is equal to 6 an minus 1 minus 9 an minus 2. Then the recurrence relation becomes r square minus 6r plus 9 equal to 0. Okay, r square minus 6r plus 9 equal to 0. Now, for this particular recurrence relation, if we solve it further, we can say that this is of the form, this is of the form r minus 3 square. Okay, this equation is of the form r minus 3 square is equal to 0, and so we get r equal to 0, sorry, r equal to 3, r equal to 3 for multiplicity 2. Multiplicity 2 means, as this is a quadratic equation, it have two roots, but both the roots are same, or in other words, we can say that r1 is equal to r2 is equal to 3. R1 is equal to r2 is equal to 3. So as the root is repetitive, this solution equation can be given as alpha 1 r1 raised to n plus alpha 2 n into r1 raised to n. So as there's only one single root. So for this particular recurrence relation, we get an is equal to alpha 1 into 3 raised to n plus alpha 2 into n into 3 raised to n. Now using the initial conditions at n equal to 0, we get a0 is equal to alpha 1 plus alpha 1 into 3 raised to 0, that is 1, plus alpha 2 into 0. So alpha 1 is equal to a0, which is equal to 1, and we get at n equal to 1, we get 6 is equal to alpha 1 into 3 raised to 1, that is 3 alpha 1, plus alpha 2 into n is 1, so alpha 2 into 1 into 3 raised to 1, that is 3 alpha 2. So we get 3 alpha 2 is equal to 3 alpha 2 is equal to 6 3, that is therefore alpha 2 is equal to 1. Now substitute these values in this solution equation. So substitute the value here in this equation. So if we substitute the value here, then an becomes 1 into 3 raised to n plus 1 into n into 3 raised to n. So the equation becomes an is equal to 3 raised to n plus n into 3 raised to n. So this is the solution for this particular problem. Let us look at another problem. Let us look at another problem. Try to solve this problem here. So let us solve this problem. I'm deliberately taking this problem because it has, here the nth term is expressed as the sum of previous three terms. So instead of a quadratic equation, we will get here a cubic equation. And so the characteristic equation minus 1 equal to 0. There's a typing mistake from my side. A negative sign is missing for minus 3 and minus 1. So if you look at this equation, r cube plus 3r square plus 3r plus 1, this is of the form of r1 plus r plus 1 cube equal to 0. And so we get three roots of this equation, where r1 is equal to r2 is equal to r3 is equal to minus 1. So the solution equation becomes alpha 1 r raised to n plus alpha 2 into n r raised to n plus alpha 3 n square r raised to n, which is equal to alpha 1 minus 1 raised to n plus alpha 2 into n into minus 1 raised to n plus alpha 3 n square into minus 1 raised to n. Now if we solve this equation using the initial conditions, so at n equal to 0, we get a0 is equal to alpha 1 r raised to, so a0 is equal to 1 and n is equal to 0. So a0 is equal to alpha 1 into r raised to 0 is 1. So this becomes, the first term becomes alpha 1. The second term becomes 0. So alpha 1 is equal to a0, which is equal to 1. So we get one value. At n equal to 1, a1 is equal to minus 1 raised to 1, that is minus 1 into alpha 1. So this is minus alpha 1 plus alpha 2 into minus 1 into minus 1 raised to 1. So minus 1 into minus 1 is plus 1. So plus alpha 2 plus alpha 3 into minus 1 raised to 1 is minus. So this becomes minus alpha 3. Okay, this becomes minus alpha 3. And therefore this equation becomes minus 2 is equal to minus 1 plus alpha 2 minus alpha 3. So this becomes minus 1 is equal to alpha 2 minus alpha 3. Okay, now at n equal to 2, the equation becomes a2 is equal to minus 1 raised to 2. So this will be square. So this becomes alpha 1 plus this is 2. 2 into alpha 2 minus 1 square. So this becomes 2 alpha 2 plus 4 alpha 3 plus 4 alpha 3. Alpha 1 is equal to 1 and a2 is minus 1. So minus 1 and this 1. So this becomes minus 2 is equal to 2 alpha 2 plus 4 alpha 3. Okay, 2 alpha 2 plus 4 alpha 3. Solving this value equal to 3 and alpha 3 value equal to minus 2. So we get the final solution equation as an is equal to alpha 1, which is 1 into minus 1 raised to n, plus alpha 2 is 3 into n minus 1 raised to n, plus alpha 3 is minus 2 into n square into minus 1 raised to n. So this is a solution for the recurrence relation with three roots. Now let us understand the concept of repeated roots, or a recurrence relation with a mixture of repeated and non-repeated roots. So let us consider that uh, there is a linear recurrence relation, A of n, a homogeneous linear recurrence relation with five roots. Okay, the characteristic roots are five. Out of, and let's name them as R1, R2. Let's name them as, for simplicity, I'll take them as capital R1, R2, R3, R4, and R5. Okay, let's assume that out of these five roots, these two roots are identical. So let's name them as R1. R3 and R4 are identical. Let's name them as R2. And this root is singular. This is R5. Means this particular problem is of three distinct roots, but the R1 is repeating twice, R2 is repeating twice once. Now, as the roots are repetitive as well as distinct, the solution equation can be written as let us now have a nomenclature. Alpha is denoted by I comma j, where I is the root number and j is how many times its multiplicity. Okay, so for example here r1 is repeated twice. Root r1 is repeated twice, means it is uh, it is two times. So I'll write the equation as alpha 1 0, that is alpha 1 1, that is first repetition of root r1, into r1 raised to n plus alpha 1 2, that is the second repetition of root r1, n into r1 raised to n, plus alpha 2 first repetition of alpha root r2, r2 raised to n, plus alpha 2 2 into n into r2 raised to n, plus plus alpha 3, the third root is non-repetitive, so it is r3 raised to n. So in such a way, we can write a solution equation for a recurrence relation which has few roots repetitive, few roots non-repetitive. Now let us look at a linear recurrence relation which is non-homogeneous. Now how does a non-homogeneous uh, concept comes into recurrence relation? It comes because of an additional term f of n. It comes because of an additional term f of n. So the rest of the recurrence relation is same as homogeneous recurrence relation, but we have an additional term f of n which is a function and which depends on n and not on the previous terms of the sequence. So such recurrence relation, these are few examples of such recurrence relation which has a homogeneous part as well as a non-homogeneous part. For example, here this has a non-homogeneous part, this is a non-homogeneous part, this is a non-homogeneous part, and this is a non-homogeneous part. So these are non-homogeneous part of the equation. Rest of the equation are the rest part of the equation is homogeneous in nature. Now to solve this equations, to solve this equations uh, solution, then the solution has two parts. Okay, the solution of the sequence has two parts, one which comes from the homogeneous part, which we will solve exactly like how we have solved the earlier equations, and one which comes as a particular part which comes. Now the problem here given is an is equal to 3an minus 2 plus 2n. 2n is basically a non-homogeneous function equal to, the solution will be given by the homogeneous part and a particular part. So we'll first solve it for homogeneous part. So we'll take an is equal to 3an minus 1. The characteristic equation is r minus 3 equal to 0, and therefore r is equal to 3, and therefore equation of the part which is for the homogeneous. Now for a particular part of the equation, that is 2n. Now if you look at the previous non-homogeneous equations, we can see that the non-homogeneous part is 2 raised to n or n square plus n plus 1 or n cube or n into 3 raised to n or n factorial. So in general what we can say that about this 2n, that this 2n is nothing but it is a uh, homogeneous part which is of the form, which is of the form like a line of like a straight line equation. So we can say that the non-homogeneous part is basically described as a0 plus a1n, a0 plus a1n, and the original equation is, the original equation or recurrence relation is 3an minus 1 plus 2n. So equating this one equation 1, this is let's say 2 and this is let's say 3. So when we equate, okay, that is from 1 and 3, from 1 and 3, what we get is that both the 1 and 3 is, the LHS is an, so we get that a0 plus a1n is equal to 3 into, now if an is equal to a0 plus a1n or a1n plus a0, then an minus 1 will be equal to a1 into n minus 1 plus a0 plus 2n. Solving this further, we get a0 plus a1n is equal to 3a1n, 3a1n minus 3a1 plus 3a0 plus 2n. Okay, so this a1n will get cancelled with this, so here it becomes 2a1n. This a0 gets cancelled with this one, so this becomes 2a0. So effectively the equation becomes 2a1n plus 2n plus 2a0 minus 3a1. Now in this equation, in this equation this equation will be equate to 0 if 2a1 plus 2 into n plus 2a0 minus 3a1 minus 3 even. Now the equation will be equal to 0 if this first parenthesis is 0 and the second parenthesis is 0. So if we say from this that 2a1 plus 2 is equal to 0, then a1 is equal to minus 1 and a2 is equal to, that is, or a0 is equal to, so 2a0 minus 3a1 is equal to 0, a1 is equal to minus 1, so a0 is equal to minus 3 by 2. Substitute this value into equation 3. Okay, so we get an for the particular part, an for the particular part is equal to a0, that is minus, sorry, minus 3 by 2, and a1 is minus 1, so minus 3 by 2 minus n. So the total solution is equal to sum of the homogeneous solution plus sum of the particular solution. So this is equal to alpha 3 raised to n minus 3 by 2 minus n. Now we have initial condition given at n equal to 1, a1 is equal to, use this, let's say this is equation 4. So in equation 4 we say a1 is at n equal to 1, a1 is equal to alpha into 3, so it becomes 3 alpha minus 3 by 2 minus 1. Okay, to solve it for alpha, so a1 is equal to uh, so a1 is equal to 3, so 3 is equal to 3 alpha minus 3 by 2 minus 1. So taking this on the other side, so 3 alpha is equal to 3 alpha is equal to 2, so alpha is equal to 11 by 6, so we get the alpha value is equal to 11 by 6. Therefore we get an is equal to, the equation 4 was, I'll write it again, the equation 4 was 3n minus 3 by 2 minus n. So substituting alpha is equal to 11 by 6, we get an is equal to 11 by 6 into 3 raised to n minus n minus 3 by 2 as a solution of the recurrence relation.